Okay, let's start. Any questions? Okay, if there is no questions, let's continue with the tutorials. So we were done some things, last things. Today, the main aim of tutorial is about Noether's theorem. Okay. So you are all familiar with the classical mechanics concept that for Lagrangian, L, if specific coordinate is absent or AXA is equal to 0, and then we have d by ds of dl by dx dot a minus, this is our Lagrange equation from the assumption that this is 0 means this goes away, and this is equal to 0 we have, and that lead to dl by dx dot a is equal to constant along the curve. Okay, so this is important. It's constant along the curve, and that you may call a generalized momentum. So you are all familiar with this. The same thing continues on the space-time. So it can be written purely in terms of the space-time metric. Now we have a space-time. We have a metric given by ds square is equal to GAB dxa dxb. So this is our length element, and the metric is GAB. Okay, you can upper or lower it, does not matter. Let's say that a specific coordinate is absent in the metric. That means, let's say that GAB is let's say x3. Okay, 3 is a coordinate here, x1, x2, x3, or x0 if you have a space-time. So this is generally applicable to any Riemannian geometry. So you could say that this is equal to 0, and from that analogy, we have a conserved quantity. That means that let's formally state this. So let us consider a geodesic. Okay, geodesic motion, what does it mean? The geodesic motion essentially means that for velocity UA satisfies the geodesic condition, or the acceleration. For acceleration is 0, and we know that the for acceleration is given by this. The geodesic motion with the for velocity UA, it satisfies the condition which is for acceleration is 0. Now let us call the give a specific name to our this notation here. Let us call or define xi a to be delta A3. Okay. Also, it means it's an example that could be anything. Xi could be any arbitrary vector, but in this case, we are choosing such that GAB xi C xi C is equal to 0. So this condition, actually what we have here, here is reflected like this moment we define the vector field xi like this. So these two conditions, this and this, are equivalent condition, but it is given in the nice form that we have as defined. So any questions so far?
Sir, I couldn't understand the last equation that you have written. Can you explain again?
No, what we say cyclic coordinate means that the Lagrangian is independent of that quantity, right? So the
Yes.
same condition reflects in the space-time as a metric is independent of a specific variable. Here it is easy to write like this, but you see that it is there is a kind of a problem here. The A does not go from all the way to 0 to 4. A is fixed here, 1, 2, 3. In the case of Lagrangian mechanics, if you have a relativistic mechanics, it could be 0, 1, 2, 3. Right? It can't be simply A because it's against notation of relativity or tensor analysis to write this because it is valid only for specific component, not for the entire thing. So that is why I have written it. Lagrangian is specifically absent, let's say phi. You have a r, theta, phi, and t, of course. So then you say that the Lagrangian is absent of phi, angular momentum is conserved, that which we know. So to write that, I write like this and write 3 is specifically the third, the phi is absent. To make it more concrete, I define my psi vector to be delta A3 as I have done here. Okay, that means that when I contract derivative of metric with the xi, then I would get exactly is the condition which is given here. Okay, these two conditions are same, but except that this is nicely written.
Okay.
Okay, so that is what we mean to say that the directional derivative of not covariant but a partial derivative of metric along the taken dot product along this vector xi is 0. The xi happen to be a coordinate, but in principle, if you rotate it by something, then phi and something r might get mixed up, and then you would have xi in some other direction. And but this condition would remain same because when you rotate thing, this would also get this our delta, this xi. A new component would have not simply delta A3, but it could have some arbitrary component. Okay, so now our goal is to look at the let's say that C is equal to UA xi A. Okay, so this is what we want to see. Okay, this is a could be same as a PA xi A for momentum. This is a for velocity. Okay, so this is for momentum. So you know these two are same, but except if you are taking the m to be mass of object, then you simply have these two are connected by constant. Otherwise, you could simply have this relation. Let's take that d capital by ds along this curve. Okay, so that is means that we are trying to differentiate this constant and take the projection along the uh, tangent vector itself. That means that take the covariant derivative, take ua psi b into ua is equal, that is this is equivalence relation. Okay, so that is why I'm taking the derivative of this thing along the uh, curve. Is it clear? This is a kind of a messy mathematics, little bit, but not too complicated. But idea is very important from the physics point. There is not much uh, mathematics as it is, but I will try to make it complicated as much I can by putting all sorts of indices. But is this idea clear? Does anyone have a question? This is very important, not just for special relativity, but in general in physics, this is important. Riemannian geometry or not, even ordinary Lagrangian, it is important, though you might not be seeing it in this particular way, but it will be very useful.
Sir,
Yes, go ahead.
sir, can you just repeat what we do after we define this CSUA psi A?
Yeah, so what I want to do is I want to show that it is idea must be already known, that I want to show that the C is constant. That is why I've given it a name, big C. So what is the meaning of constant? So in the classical mechanics, it is very easy to show that you have a time is a parameter along your curve. So you have a t, and then you have anything d by dt is equal to 0 would be constant of motion, right? So this is a bit tricky in the Riemannian geometry. How do you say something is constant of motion along a curve? So for that, what you should do is you have to take a covariant derivative of a vector field or variable phi or whatever you have, and then you have to take a directional derivative along the tangent itself, where ua is equal to dxa by ds. Okay, so this is a tangent to the curve. So you have a curve here, you have a tangent or the velocity 4a dxa by ds. Now you take the gradient of this scalar field and take the dot product along the velocity vector. So this is how we got the acceleration. If you take the, let us look at this expression. Okay, let's look at this expression. What is this expression? This expression is you take the u itself, okay, ua itself, take its directional derivative or covariant derivative, take the dot product along u itself and set that to 0. What is this? We have seen that this is equivalent to acceleration. This is the acceleration of particle, which we also, after some simplification, we would get du by the notation which we used is this, or we could simply write it as d square xa by ds square plus gamma a b c d by dx a by ds b and dx by ds c. So we have seen that is a geodesic equation which you get. Now if you want to show a specific quantity is constant along this curve, then you simply have to take the directional derivative of that quantity along the curve. What is the directional derivative? You take the general covariant differentiation and then take dot product along any given vector. In this case, that we want to take a directional derivative along the tangent vector. That is what gives you directional derivative along the curve or the trajectory of the particle. So that you can obtain by taking the dot product of the covariant derivative with respect to the tangent vector of the curve. So that is generally true for what is the meaning of a directional derivative. Directional
Sir,
derivative is a general concept.
sir, in
Yes.
this dc by ds, shouldn't the first ua be ub, as in you have written nabla
Yes.
a u?
There is a typo here. Not
Yes, sir.
typo, right over. Okay. Okay. So this is the expression should be. Okay. Yeah. So let us go ahead. Is it clear, or is there is a still confusion about directional derivative?
Sir, why
Or
the
that
acceleration is zero? Can you again?
no, acceleration 0 is assumed. It's a geodesic curve. So for geodesic curve, it is assumed that the acceleration is 0. That is the definition of the geodesic itself. Is that the question?
We are considering this in the absence of an external force. So
Yeah, so this is valid only for the force-free or free particle geodesic motion. Otherwise, acceleration will be there. You will see that we are interested to find the conserved quantity which satisfies the Lagrange equation. Satisfying the Lagrange equation itself means that the geodesic equation of motion. Yes, is it okay? This is an important concept to understand. So please do ask if you have some doubts. Should we go ahead? Any questions? Okay, let's simplify and redefine the whole problem. So what we have a vector. Let's not worry about anything about it. We have a vector called xi a, okay, and then we have a geodesic motion. Now we are taking the dot product of the momentum or the for velocity of a trajectory with the given vector which is called xi a, and that is what is our scalar, which we call it a c. And now how we want to check how this is being propagating along the geodesic or its directional derivative along the geodesic. So that is what we want to do. Now let's expand this. Mathematically, it's simply the product rule. So you have to have a xi ub. This let's multiply here, otherwise there will be a problem. And then you have a ua. Okay, then the second term would be del dot a xi b u b and ua. Now can someone tell you can identify something and simplify something? Any of the term you can identify here?
So the first term is the acceleration times
Yeah,
the
first term is the acceleration, so that goes away. So this is 0 because we have already assumed that the ua is 0 by this equation. That is what is the acceleration of the particle about, and then you left with this term. So you have del A xi B plus UB UA. Okay, so that is, let us try to simplify this. We got to take this differentiation. Let's remind us again. Let's take this form of the metric, no, xi A. So you could call it anything. You could call it n if you want. And let's try to lower this index. Okay, let's try to do xi A, that is equal to GAB xi B. So this is equal to GAB delta B3, and this is simply equal to GA3. So G3 is representative here. You can call it any n. I am not giving it an index specific name in order not to confuse it with the vector index. Now let's try to calculate this. Once we have this, let's try to calculate this term. We are not actually calculating this, but we are actually calculating xi b into ub ua. Okay, so this is what we are going to calculate. So I'm doing it a bit long way to show you certain things in between. How does it reflect in terms of metric component? Otherwise, this calculation is too trivial. If you look at what condition you should impose on the xi, it is straightforward. But let's do this in this long brute force method to relate it to the metric coefficients. So let's write down this this covariant differentiation of ZAB, and that is equal to what we have here is first is xi A, xi B, ordinary differentiation. I think there is going to be a minus sign here, and gamma ABC, and then xi C. Okay, so in order to get the explicitly connection with the metric coefficient, now we have to assume the relation between the coefficients. So all these things are valid only in the Riemann space now. Moment we assume gamma as this form, you no longer can keep this in the general space time. So that's okay. We are not too much worried. The Riemann geometry itself is complicated enough for us. So we can expand gamma in terms of the partial differentiation of metric, and that is what you get. So this is what you have. Now let's finish this. Let's substitute this into delta xi b is equal to dA xi b minus gamma CAB xi c. Now we can substitute all of this to get a lengthy algebra. GCP. At this stage, it is a bit of a mechanical, but it is have to be done. And there is a xi c here. Now we can simplify some of these terms. First thing is to notice that this is there, and this C and C is simply pulls this up. So let's write that. So what I have done here is taken this and xi c outside, and then write it as half xi p. Now you have three quantities here. PB xi x a plus GPA xi x b minus GAB xi x p. Now you see that from the assumption which we made, we assume that the following condition which we have assumed, that we assume that GABC GXC xi c is equal to 0. So which is assuming that the directional derivative of the metric along the vector xi is 0. So this is not covariant derivative, it's a partial derivative. Covariant derivative of metric is 0, so there is no need to worry about it. So we get that to be 0. Okay, so because that P and that goes away. Now you look at what remaining. Okay, so let's first look at this term. We have said that somewhere here this xi a is equal to GA3. Okay, so we can substitute that, and then we would get that this is equal to GA GB3 minus, well, we could call it simply taking the dot product with the xi a, or I can simply call it C into xi c. Okay, that is what we have. This expression, you can simply look at it here, get this, or simply pull this out and play around with indices and you can get this. And then you have these two terms. Now look at these two terms, A, B, P, A, B. P is common, which is taken dot product. So this makes it, this term is completely symmetric. So this is equivalent to, because it is symmetric, you simply get xi p gxa g bp. Okay, these two terms are same, so this cancels out, is equal to 0. So what did we just prove? We just proved that UA xi a is equal to C is a constant of motion. Constant of motion means its directional derivative along curve is 0, or it is a conserved quantity, or whichever way you want to say. So this is essentially Noether's theorem, what we have in the Lagrangian, which is generalized to any space-time. Okay, so is this clear?
Sir, you're taking xi c outside because it's a constant.
Where I have taken xi c outside? Here?
Yes,
No,
sir.
I am, see, we have a constant, but we have this relation too. You can simply lower it and raise it as you want. And then because it is defined like that, you can simply flip it over. Yeah, it is in a way, it is constant.
Okay, sir.
Sir, can you explain why you have taken that condition that in the left hand side that is written in red means how you have
That is
taken
the
that?
assumption.
Yes, sir,
That
means
is what
how?
it says, is that if it is a Lagrangian is independent of that coordinate, that means the directional derivative of Lagrangian along that coordinate is 0. The more vectorial way of saying is the directional derivative of Lagrangian along that coordinate is 0. But why coordinate? You could choose any vector as long as it's a directional derivative of Lagrangian along that vector is 0, then the generalized momentum along that direction is also conserved. Okay, you don't have to align your coordinate system along the cyclic coordinate. You could have any direction as long as you can identify the vector corresponding to the cyclic coordinate. You can take the directional derivative along that and set that to 0. So that is a basic idea. Okay, any more questions? Okay, if there is no question, let's go ahead. This leads to, this is a very easy to generalize further. So what is called, this is a completely geometric concept now. So we go ahead and do this, what is called killing vectors. So let us now say that let's say you have a vector field xi a, okay? Then it satisfies the condition del b xi a plus del a xi b is equal to 0. What does it mean? It means that you are taking the covariant differentiation of that vector and then you are symmetrizing this and then setting it to 0. That means that in this notation, symmetrizing this and setting it to 0, that means that the covariant differentiation of a given vector is completely anti-symmetric. In words, the covariant derivative of vector xi a is anti-symmetric. Okay, then for a geodesic, UA xi a is equal to C xi is constant along geodesy. That means that UA UB equal to 0. So this is a theorem and the vector xi a is called killing vector. Okay, so it's a further generalization of what we have seen in the Noether's theorem, that it is no need to worry about taking the directional derivative of metric with respect to this vector field and setting it to 0. There is a easier way of doing it, and that is what it says is a killing vector. So the idea of this is fairly simple. There is nothing much to do actually. Let's call the C xi is equal to UA xi a, okay, and U satisfying the geodesic equation. So this is equal to 0. So if you want to put an and in between. Okay, these two conditions we have. Now we got to take a directional derivative of this C xi. Let's take UB C xi, okay, multiplied by UB, that is equivalent to d by ds of C xi. That is what we have to show, that is 0. So let's go ahead. Let's do this thing. Substitute this. So we have a B, and then we have a UA xi A, and then you have a UB. That is what we have to find out. Let's do the chain rule business. No, not chain rule. Product rule business. UB, UA, this one. You have seen earlier that this is 0 because of the simple reason that this with this gives the geodesic condition. So this is a geodesic condition. And then this goes to 0. The second term remaining here is that del B xi A into UA UB. Now you see an interesting fact here. We have shown that this quantity, let's look at this condition, okay? That means symmetric part is 0. Now you see that this is a symmetric tensor and we are multiplying this. So if the symmetric part is 0, and then this term would be 0. So this is equal to 0 because of the symmetric term, because this is a symmetric tensor, this is a symmetric tensor, and this automatically gets symmetrized. And when you take a dot product of anti-symmetric tensor with the symmetric tensor, we would get a result 0, and that is what we need to show, that the d by d, capital D S of C xi is equal to 0. And we can write it more permanent ink, d by ds into C xi is equal to 0, or constant of motion. So this is what essentially means that the killing vector, it gives you the conserved quantity in a given geometry, and the way to figure this out is by solving this differential equation. This is essentially a differential equation. Now you see that in the earlier derivation what we did, I have just simply hidden this so that you did not see it. Again, you see that from this step, okay, if you have known symmetric property here itself, we could have done it. But I went ahead, and that time goal was to show that if a metric is independent of a certain directional derivative of a metric is 0 in along some vector, and that would corresponds to this thing is 0. So what does it means? That this identifies the two things. Killing vector means that the directional derivative of metric is 0 in that direction. That is, these two give rise to the same condition. You can combine the algebra given in the previous derivation and current derivation. At this step onwards, you can show that this is exactly comes out to be the directional derivative of your vector along some direction. Directional derivative of a metric tensor along your arbitrary vector is going to be 0, which is another definition for the killing vector. But geometrically, this one is more appealing. So you have to have this as your condition for the killing vector. Killing vector means that the metric is invariant under the direction. That means the directional derivative of the metric in that direction is 0. So if you make a translation along the direction, then the metric is not going to change. That is what it means, the directional derivative. It is remain constant along that direction. Okay, so this is an important idea. It will take maybe some time to sink in. So you want to ask some questions, doubt, clarifications?
So, sir, it is a vector that gives a direction along which, if we evaluate the directional derivative of the metric, then it is 0. That is
Yes.
what you mean, right?
Yes, or another way to say is that the metric is invariant under that direction. It's the same way. If the directional derivative of metric is 0 in some direction, that means metric is not going to change if you displace your coordinate along that direction. How do you take this is a partial differentiation which you have taken. So it means that you simply move, take a point in that direction, subtract between these two, and take the limit them going to 0, so that remains constant, that is 0. So that means metric is directionally invariant in that direction. There is a geometric way of telling is through the equation given here, but that corresponds to you can combine the two derivation and show that it is same, that metric partial differentiation or a directional derivative of metric along the direction is 0. So any more questions?
Sir, hello.
Yeah, go ahead.
Sir, can you explain how the last term like went to 0 after the symmetric conditions?
This one?
Yes.
Okay, so the two things here. First thing is that this is a symmetric tensor. This is the obvious thing to do. So if you do UAB, that also can be written as half times UAB plus half times. Let me. Okay. Let me move it between this. Plus UB UA. So it is same. You see that there is no way, no need to write it like this. These are the same vector, so they are symmetric. Now you see that our condition, what does it say? That it means that del dot xi b plus del dot xi b, this is 0. Okay, now I can put that into this equation. So this becomes anti-symmetric and this becomes symmetric. So these exactly cancels out because of the properties of them. How do we do that? Because we have written like this. Okay, so we can write this as a del dot b xi a, okay, into half. Let that get rid of that half, UAUB plus UB UA. Now you see that this is a symmetric, and this actually can be written as a anti-symmetric. That means xi b, no, that means that xi b xi a also equal to minus xi xi a xi b. So if you consider this property and this, so this exactly cancels out with these, and this give rise to 0. So the dot product between the anti-symmetric second rank tensor and the symmetric second rank tensor is always have to be 0, because one term get exactly compensated with the other term along the off diagonal element. Is it clear?
Okay, sir. Yeah, thank you, sir.
Yeah, think about it. It's just about rearranging the indices and using the properties of symmetric and anti-symmetric tensor, which we have not done too much in this course. But you can see that the multiplication of a symmetric matrix and antisymmetric matrix, and the trace should be 0.
Hello.
Yes.
Sir, in the not directional derivative, it's covariant derivative of xi b.
Yeah.
That, can you go to that part?
This one?
No, before that.
Yeah, this
Here,
one. Yeah.
here you have said that the last term is symmetric under A and B.
Yes.
So you just write it here. I mean, how is it? I mean, that term is symmetric. That's fine, but that doesn't mean that both are same.
Which one? Which one? Okay, I think you have picked up the right spot. So which term you have a doubt?
The second, that bracket term after cancelling yes.
Yeah, actually, it turns out that you can do this calculation and these two terms would exactly cancel out. Okay, so other way is to see it in a simple way is that I take the symmetry property of this, and that would have this.
Yes,
which
that
is
that will give 0. That will give 0.
Yeah.
But
and
here, but specifically, nabla a xi b.
This, no, this may be not correct. This actually get cancels out with this.
It's not clear.
No, this term would cancel out with this. So if you look at this, where is this? Here only. So you have this term, and then let us see what happens. So D, we need something. D A xi b. Let's do the calculation. It's actually these two terms cancel out. That is what the algebra is about. Now what happens there? We could take this. Actually, in that G03, you have to put that. That is a problem here, but we can simply do this this way. So what do we have? We have a G A, G A B, xi. No, A is coming too many times. So now we will have this GAB, GBC, xi C, okay, plus GBC, GA, xi C. Now what do we have here? We have this term is what we need, and this is a term which we have, GBC, GBC. Okay. Now we know that this term is symmetric between these two indices. Then we can also have this term exactly equal to GB. What was that? Oh, did I make a mistake? Okay, no. GABC into xi C plus G B C, no, B becomes A, and then xi A, no, xi B, xi C. Okay, so these are the two terms which we have there, which would have, in addition, we have one more term here. So this what happens to this term? So let's see. C is same, then GAC, GCA. So again, one gets into cyclic condition, one need to say that this term is a symmetric, so one has to essentially get rid of this term by symmetrizing these two indices. So that other way is to take that in this case ZC, we have assumed a constant vector 0001 whose component do not change. So this would go to 0 because of that. And then you left with this term, which would be symmetric because of the nature of the equation. And those two would cancel out with these two.
Yes, I mean after symmetrization, those cancels. But
Yeah, so that can be done here too, right? Because symmetric property of partial differential have to be considered.
symmetric property of partial differential.
No, that is true, right? It may or may not be a tensor. That is not what we are worried at present.
No, but we are
Because,
not using that symmetric property of partial differential here. I mean, when partial differential comes, we use that.
yeah,
But here only the del A or del B things.
no, what
How
do
does that
we
properties?
can take the, no, we can simply rotate the index and add them up, right?
That goes to 0, but that doesn't mean that each of them is individually 0. That's
No,
why.
no, no. That is a slip of tongue or whatever it is. The individually they are non-zero. That's not possible because you see that what happens here. Look at this G A P B X A and G. Let's take, suppose you have a metric which does not depend on the time and does depend on R. Okay. Then you say that one would take the value of time and the other takes the value of R.
One
Then
goes to 0 and one doesn't.
yeah, that other becomes 0, one does not become 0, so they are simply not equal to each other. So it's
So
just that
that's
total
symmetric.
sum of them goes to 0.
Yes. That's what.
Yeah, so that is a underlying thing, that is just the slip of this thing,
Okay, it's
flip of tongue rather than slip of tongue. Okay. So, but one don't have to go through all that. It is just necessary to show that this condition actually the symmetric nature of this condition essentially means that this directional derivative of metric is 0. But if you don't want to even do that, you can simply use the midway relation. That is no problem. One can simply use this relation. Let me write it down. You could simply say that xi A GBC dot A plus xi A comma B G, A, C, plus xi a. Oh, comma is a notation which is used by the Narlikar's book, from which I am copying. So this is AC, and what happens? G A B equal to 0. So in our notation, it simply means that the del G B C A xi A plus G A C G B xi A plus G A B C xi A equal to 0. So this is the step which we are essentially reached at. So that one can show that it is also a same. So there are a couple of ways of doing it in the same way. Okay, but this is here. This is a condition which you can actually expand this in terms of the normal covariant derivatives, in terms of the partial differentiation and gamma symbol, explicitly express gamma symbol in terms of GABs, and then you would simply get this. That we can do next. But yeah, think about it. We will take a short break, or if you have some question you can ask, or maybe we could take a 5 minutes break and then we can do the derivation. We can show that the expression given here, let me see, where is my... So we can show that this equation is exactly equal to this, so that we can do, or I can let you do that. You can take a 15 or 15 minutes to do that. Can you all do that? Let's take a break of 15 minutes or so. Meanwhile, you just simply show that this condition is also equal to this condition. These two conditions are same. Okay, so that is a part of this thing. Let me just take a short break. We will join at 12:15. If we have some time, we will do some example. Otherwise, if you have some questions, we can ask, and then we can disperse. Let's take 15 minutes break where you finish these calculations. Okay. Any difficulties? Is it okay? You all could do it?
No, sir, I've stuck somewhere after using the definition of covariant derivative.
Okay. Anybody else? Let's try to do this. Where is it? Okay. So you have del A xi B. Let's start with this. Okay. Can you see the screen?
Yes, sir.
This one. Okay. So now we need covariant differentiation. What is a covariant differentiation? So this can be written as G A xi B minus gamma C A B C Z C. Okay. So this is a straightforward step. Let's do one more step ahead. Let's express this as a half. What is gamma? Gamma is gamma CAB we need. That can be written as a half GCP. Okay, into there are three more terms coming. That is G A GPB A plus GB GPA minus GP GAB. This is a mess. Okay, so let's rewrite below. So G A xi B minus half GCP into GA GPB plus GB GPA minus GP. Now we are not assuming that the dot product with this guy is going to be 0. So we keep that term because we are expressing the slightly different algebra here. Earlier we have assumed that this term going to go 0, so that we will not make it 0 this time. So you have a GAB, okay, minus half times xi C, okay, into GA GPB minus plus rather GB GPA minus GP GAB. Okay, now we see that what we want is the del A xi B. Okay, that means we have to symmetrize between the index. You can go through the whole calculation of flipping B and A and then doing all that thing. But instead of in a compact notation, you simply say that we do this on both sides, symmetrize on both sides with the index B, A and B. So you have A here, okay, There is another notation here. It doesn't matter in this case, but you might as well know the notation. I put a vertical bar and then P vertical bar B. Okay, I will not explain what it is. This
So I
is
thought
just
we are going to exchange the indices A and B and then add them together. But
yeah, but P is not taking part in that. Okay, so that's why P has been put inside the bar or fixed it. So that is what is we do. So what does this index this PB of metric or any this thing? It simply means that half A APB plus ABPA. Okay. In this case, it doesn't really matter. I can flip the B and P and first expression, or I can flip P and A in the second expression. Then they would lead to same thing. So, okay, let's go ahead and see what do we need next. So what do we have? A here, BC, A here, CB. So this is a symmetric between these two. Okay, so that is, and this is symmetric between these two. Okay. What was a mistake I made here? Can anyone figure out?
Gamma P. It could be gamma P instead of gamma C.
Yeah, so gamma P, is it? No, Xi.
yes, sir.
Sorry, Xi.
Xi P should have been, not Xi C, or this messy expression I don't want to rewrite in terms of C. Okay, so this is it. So we have it here, probably what we want. Now let's look at what all things happening here. This is already symmetric. There is nothing to do here. Agree with that?
Yes, sir. G is already symmetric.
Yeah, so that just going to remain same. And then you have a ZP. So that is what is the term about? This term GAB. Yeah, so these two terms are coming here because of this. What else we can do? Anything else?
Sir, I actually don't understand how you directly symmetrize it as in from
Okay,
the first step to the second step.
let's do this. What do we have here? So we have Xi A, Xi B, right? That is what we have written as A Xi B plus minus half. Now we know we need not do the same mistake here. GA, GPB, and GPA minus GP, GAB. Okay. Now what I say, I interchange index B and A, I can do it because nothing depends on the what you. No, your voice is not clear. Can you?
So when we write it in terms of B, del B Xi A, we'll have the Riemann tensor, right? Gamma
No,
C A, that would be equal to gamma C AB because of the symmetry of the Riemann tensor.
Here, no, not here. So that comes when you do the see what we are doing here. We are let me what this notation means. Let me write it. I think there is some confusion. Let me change the color, or let me take a fresh page. Riemann tensor doesn't come here as of now. So what does this mean? This means that
Sorry, sir. I meant the connection formula. Connection
yeah,
coefficient.
okay. So if connection coefficient comes, but we have replaced that with the derivative of metric, right? So this we have this one is put in.
Yes,
So
sir.
far,
So what my point was, so when we write the similar expression for del B xi A, we'll have gamma C B A,
yeah,
and the gamma C B A is equal to gamma C A B.
yeah,
So so when we do this this addition,
yeah,
the symmetric operation, so we'll
yeah,
just have a two factor. It would be minus 2 times gamma C AB times xi C. That
yeah.
was my point.
But this won't help us prove that these two are equivalent unless we write it in terms of metric.
Yeah, that has to be done. So the idea is to express in terms of metric. So the way what he says would be helpful only in
And
this.
after that we can
Yeah,
replace
substitute.
the
So what he
metric.
means, okay, let me state your problem. We have written xi b minus gamma, I think p, let's say, or c, okay, ab xi c. Now let us symmetrize this. Okay, we can symmetrize this, we can symmetrize this. Now we know that this is symmetric, that is going to be same GAB, xi b, because any partial differentiation is a symmetric, and then this is also symmetric by the virtue of gamma's lower index in the Riemann tensor, and this we are setting it to 0. Okay, so this, once we have this, this is exactly what we get here too. So then you can simply write it down, expand this expression in terms of gamma, and then you would get the relation what you are looking for. Is that what you were saying?
Yes, sir.
Okay, so that also can be done, but this is a long algebra, so is to get used to it. So there are various methods. It leads to confusion sometimes. Sometimes shortcut often leads to the problem which you have seen earlier. Those kind of things might also arise. But here it is a fairly neat stuff you can do, but eventually we are also doing same thing, except explicitly expressing this. You see that, okay, that we will see it leads to same thing, because there is this tends to 0, and then you have all these things you have to simplify. Now there was much different level of question was there. Let's keep it aside here. So is it clear whether I can need to do it explicitly, or is this expression okay?
It's fine,
Somebody
sir.
asked, how did I do it directly? So I can do it. I can explicitly do it. I would get simply same thing. There is no, oh, this color. So I get ZA minus half, P remains same. And then I simply flip here between A and B. So you don't have to do it explicitly each time. All it means that symmetrizing can be done on both sides of the equation, and then that would lead to same thing, because you are simply adding or subtracting. It's a linear operation. So any linear operation does not alter anything. So that symmetrizing, anti-symmetrizing, all those operations are linear operations, so there is no thing. no problem. You now add these two. Okay. Now this leads to 0. Then you have this equation A xi b plus z b xi a. Now you have 3 terms here. Now the symmetrizing between the gammas would the same reflect as this. So this is a symmetric. You can see this between A and B. Now you can see the changing A and B would not change these two. So that is not going to change at all. So we still have the same form. We have half xi p, and then we have a one term here. This is already symmetric. So this this equivalent to adding up two symmetric term, which would simply give it to B. Let's leave it if you have a confusion about it. You can keep them, and this is a symmetric term too. So the that is exactly what we have now. We have a G A G P B plus G B G P A plus G B G P A plus G A G P B, and then these two are same terms. I could simply add them up, and then I would get 2. Or if you want, I don't have space here, so I simply write this as GAB. So you see that all other terms are symmetric here. It is all essentially symmetrizing between the two indices, so that would simply add up. Same thing. So you have G A xi B plus G B xi A, simply not plus, here minus, time xi p into GP GPA plus G. What is the next term?
D A G P B.
Okay, so this is the kind of a term which we have ended up. Let's get this term copied someplace. To the next page. Okay, now this up. This has to be 0. That is a condition of symmetrizing. And then we have this expression here, which we want to show. Okay, let's put it slightly. The index, there is a problem. So let's write down this, rewrite this with the same index. So A is a dummy, we don't need. We are using it P as a dummy. So xi P, GP, GBC plus GAC, differentiation of this xi A plus GAB. What did I again make mistake? I was not careful about this. What did we do? AB. Okay. Okay. Now let's AC. So G, A becomes P, and B becomes A, and C becomes B. A, B. A becomes what? P. B becomes A, and xi B, xi P is equal to 0. So these two, you have to show this to be equal to each other. Can you do that? Now you see that, so let us take this term and this term. Okay, that is we already have. Agreed? No?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now all you need to do is you see that this term and this term. Oh, okay. Which term and which term? You simply have to pull xi in and xi out. Okay. So that is what you got to do. So that is done by a simple exercise here. So you say that G, A, B. Okay. So that is what you have. Do you prefer to have this? Okay. Now let's write it as GA, GB, P, xi P. Okay. This leads to GA, GBP. Put the bracket explicitly, plus what is the other thing? GBP, GA, xi P. Okay. So that is what we are going to substitute in our expression here. So let us keep this in the box. This is what we want to show. So let's take this term. Okay. I do this, then play a trick, and then expand this. So then this term is equal to these two terms. So let's substitute that. Now what we have is first term as G, let's make it a little thinner, G, A, G, B, P into xi P plus G, B, P into G, A, xi P. Okay. Now you see that what we have here, this term is equal to this term, right? Are you following it?
Yes, sir.
Yes. And then there is this term remaining. Let me write down fully if you find it. ZB, xi A minus xi P into GB, GPA A plus GA, GPB minus GP, GAB. Okay, so this is done. So we can see that this term is cancelling out with this. Same way, this is going to produce a term which is going to cancel out with this and producing a term GA xi B. Okay, it is a straightforward calculation. You replace A and B here, and then that is what it would happen. So eventually you end up with the term ZA xi B plus ZB xi A minus minus plus, that is ZP GAB is equal to 0. So that is what is the expression which we want. So that is the condition on xi in terms of partial differentiation. So you can take this and work back, and then you would get this expression. So both ways it works. So that is what we have here. So earlier we have used a specific case that the directional derivative of xi is 0 along certain vectors, and that certain constant vector. Okay, that you have to remember. So that last case we got because it's a constant vector, we have assumed this 0, and the directional derivative is 0. So that is what happened in the earlier thing. So you don't have to go through this, that you can simply assume this condition, and then you would simply get this from this. Okay, this you can show that this is what we have done. Okay, so this is just algebra. There is nothing really anything into this. Okay, we have only few minutes left. Any questions? Is that okay? This is only one step, is that you have to play around with this indices here at this point. Otherwise, it is fairly straightforward.
So the motivation of doing all this was to show that there is a certain symmetry by taking this vector.
Yes, yes. So this shows that you can show that this is actually coming from the fact that if you take a metric GAB, okay, and then you have a x of P, let's call, and then xi P, and that would be equal to this. So you can do that algebra. I am not going to do it. So it's fairly straightforward that this is equal to 0. That means the translation, the transformation of P plus xi P leaves the metric invariant. Okay. The importance of killing vectors is the importance of conserved quantity in the Lagrangian mechanics. So if you don't have them, you cannot simply solve your problem, reduce them analytically to first order differential equation. That can be done only presence of the killing vector. If there are no such things, then there won't be possible to solve the problem. So you have a spherically symmetric case, you have LZ is conserved. So that is in the case of a spherical symmetric, the last time we wrote a metric, ds square is equal to f of r dt square minus f of 1 by f of r dr square plus and minus and so on. That's not relevant. So here one killing vector xi a, which is called the time-like killing vector, which is 1 0 0 0. So you can see that the metric is independent of time. So this leads to the is equal to delta a 0. The other one is which is usually called a rotation or actually around the axis, which is angular momentum, leads to conservation of angular momentum. The first one leads to the conservation of energy, second one leads to conservation of angular momentum, and that is how you can have the conserved quantity because of the killing vectors. Okay, any questions? So that is one small exercise I want you to do. I probably did not get time to do it on the sphere, but exercise is basically to do with the one of the relation with the killing vector to the Riemann tensor. So that is much interesting equation because it leads to a lot of finally implication of using the killing vector to actually how does it helps to even in Einstein's equation. So we could not count the killing vector. So I think that is a straightforward considering the symmetric property of it or anti-symmetric property of it, not symmetry. So you see that the symmetry, how many symmetric tensors independently are allowed. If you find that, that would be n into n plus 1. But let's leave that. But one exercise I want you to do is that the del A, del B, okay, times xi c. Okay, so this leads to minus r p. Okay, then you have what is that b a and then c xi p. Might have flipped up some indices, but that would lead to only negative sign. No, this need to be A. This need to be RP. C is okay. So A, C, and B. This is P, xi P. Okay, I want you to show that it's fairly straightforward. There is nothing much to do. You know that this property of anti-symmetry between A and B, see, if you do, it can be expressed in terms of Riemann tensor, but you know that the killing vector satisfies the symmetry property, or rather anti-symmetry property, that you can plug it in and then you can get the relation with the use the properties of Riemann tensor and you should be able to get it. Is the exercise clear? You just have to show that, because I know you have much easier way of doing it. Simply search the property of killing vector connection to Riemann tensor in the Google. Okay, any question?
Sir, can you go scroll up a bit? Go to the last page, please.
No, scroll which way? I am not able to.
The last page, page 5.
You are able to see page number, is it? Okay, previous page.
Yeah. Yeah.
Okay. Okay.
Can you explain once why the XP plus chi p that leaves the metric invariant?
This one, is it?
Yes, sir.
No, this is the expression. You see that what we are going to do. We are going a coordinate transformation here. X prime A is equal to X prime X A plus Xi A. Xi A is a vector. And then see how the metric transform under this transformation. And then that would be the condition given here. So that means that the transform metric is same as original metric. That metric is invariant. So that means that the killing vector leaves the transformation invariant. That is what it says. Just a minute, in case something connected with the hello. Yeah, I am speaking. Okay, so that was not an important call, so you can. So is it okay? Okay, so any question on this?
Sir, for the access that you have given, we can use the properties of the Riemann tensor that you had derived in class, right?
Yes, you have to use the property of Riemann tensor because that combined with the properties of killing vector, which gives to this equation.
Okay.
So the importance comes with the next when you construct the Riemann tensor by contracting these two, then you would see that this contraction would happen. This actually corresponds to del square or your box operator acting on xi c, which gives you the Riemann tensor, Ricci tensor taken dot product with the killing vector. So this is a quite a useful thing, but let's not jump the train. We may not even talk about this further into this course, but we are only exploiting the usefulness of killing vector from Noether's theorem point of view to get the conserved quantity for equation of motion. We are not actually looking at its implication into the Einstein's equation and so on. That is also there, but it is probably beyond the this thing syllabus of this course. Okay, any other question? Okay, so let us, I don't know this, you guys have tried some proctoring system exam last time. Did you get the chance?
No, sir.
No, sir.
No, sir, we didn't get.
You have any exam tomorrow, day
Sir,
after?
we have one mock test scheduled for today, but only people who have a midsem on Monday will be taking it.
No, Tuesday also, I think incorporated. Monday and
Not,
Tuesday.
not today, sir. We were told that only till Monday.
Oh, is it?
The next batch would be either tomorrow or day after.
Okay, I will check with them. You are actually Monday and Tuesday supposed to. You, all of you are supposed to get the invitation for today's mock test. I will check with them. Okay, so whatever be the number, everyone has to experience it. It is a new system. So one thing is I suggest is that keep calm. Okay, don't get panic. If something goes wrong, you have those numbers, you call them. I know it's very difficult, but somehow this has to be suffered. Okay, so if there are nothing else to ask, let us stop it here, and then we will continue after the exams.
Sir, you said that somehow we have to suffer this, but is it really worth suffering? I don't understand the point of doing this, Proctor, because it is not very useful. People can still cheat. I can find you some methods where people can still cheat. I don't find it worth
Yeah, no,
suffering.
that can happen even in the classroom itself, right? It is not my decision. It's basically done by the Senate. So it turns out that if you are good enough, you can cheat any system. That's all right. But what it says is that, about the cheating, there is one principle you have to always follow. So if you are good at cheating and whatever it is, it doesn't matter whether you cheat or not. Everybody cheats. The point is, smartness lies in not getting caught. Okay. So the current system was rather too trivial for everyone to get cheated and not get caught. So this probably would put restriction on that. So it would basically not allow, it will record your activities, your what you are doing and so on. So if you have done something, it is likely that the system will record it, including the opening browser. It may not warn you, but it will keep a record, and it
That is
will.
true, but it comes with many other unnecessary chaos that may be attached with it. So it should be a
Yeah,
balance, and I don't know whether this will be a good idea considering that the last time mock went quite wrong.
no, last time it went wrong because of some different problem. This of all these things, last moment preparation. That is what caused. System is fairly okay actually. It is not that bad, but the problem is that we have not given them information. We gave them information at very last moment. They got just an hour or two to prepare list of people and so on. But let's see today's mock test, where it has information has given to them yesterday, so they have prepared the list and see how it goes. I'm not sure whether it will go smooth or not, but do try it out, those who got invitation, and pass your comments on to either your representatives or to the academic office directly. Yeah, I don't know whether it is worth or not worth. It is something which is have to be done by, decided by, at some stage by somebody, because people felt that all things are going wrong. So it actually meaning we should have cancelled all the grading system during the pandemic, but somehow that could not be done. Okay. What is the question? Do we need to submit the exercise today along with the tutorial? Yes, it wouldn't take you more than 10 minutes to do it. Okay, so you write it at the end. It's not something very hard exercise. So I have no comment whether the genuinity of, whether need of such system. It would be well, we could try it out at your cost.
Yeah,
Not
I'm
at,
just giving an opinion. I'm not whether to judge
yeah,
anything.
no, I'm also telling you that yeah, we could just simply try out, but the cost is you are paying, not me. It is unfortunate that that is what is happening in the system. There is no way we can counter that.
Actually, there are some ways where you can Like instead of canceling the grading system, grading methods itself can be changed. Not sure how it can be done for such a large class, but smaller
Yeah,
class.
no, actually, you see that it is quite stressful for both sides. I agree, because you see that you might think that we are just sitting and preaching and so on. So our life itself is fairly stressful. All of us have our research which need to be pushed. Every a few months we are asked, what did you do? Every end of each year we are asked to submit reports. What did we do? Research have to go on. Our collaboration have to be kept up. We are working with people outside. So all that thing, the teaching, if it takes more than 40 hours a week, then we are basically done, right? That is what it takes currently. If you want to keep 4 or 5 videos at a this thing week, then it would basically take more than 40 hours a week. So it is difficult to have an evaluation which basically satisfies everyone, or to check and done with the given time. So each one has its own drawbacks. So this is a kind of you are younger people, you got to test all this. This is going to be probably some kind of a future where you will have to have a evaluation done, maybe attend some online courses outside. It may be training in that way. So take it as a positive. There is always some negative aspect to it. But of course, I agree, it is stressful for you, especially first few minutes when you log in and don't understand what is happening. That would be for the first test which you are taking, or if you have taken mock test. I suggest everybody take mock test to understand. Otherwise, it can be it's not that it is too hard, but the problem is if it is obscure, even if it is simple, then you won't know what to do.
Sir,
Yeah.
can you allow us to submit scanned PDFs through VLearn
For what?
for midsem?
No, that system will have, this is going to be a descriptive type. Descriptive type is exactly, they will let you a link to upload your PDF file. It's the
But I
same.
mean, the document showed that, I mean, we have to like show our this pages to the camera, and the camera will snap
No, no,
photos of
no,
it.
no,
So
no.
actually, there was another meeting about this yesterday, and as per that, we can submit a PDF. Like it
Yeah.
hasn't been officially communicated so far, but from what I've been told in the meeting, we'll have a provision to submit a PDF.
Yeah. Even in the last, I don't know if somebody of you managed successfully log in and take the test. Even in the last mock test, there was this thing to upload. What is okay? At least for this test, I can tell you what is going to happen is that you can simply scan it. How do you scan it on your mobile or whatever you can do? That of course, system might saying that you are fiddling around using mobile and all that. Ignore all that. That will be recorded and given to us, but I will ignore all that warnings. So you simply scan it on the mobile into a PDF file, and single PDF file you upload onto this site. That's what's going to happen. There's not going to be any confusion. There is going to be a single question paper which has as many questions you want. Write it all them in the usual style which you do. At the end of your exam, simply scan it using your mobile. Either you can directly upload using the mobile or transfer the file to your desktop, and whichever you want to do, you can do. There is going to be a single PDF
Yes.
upload.
Yes, sir. Regarding that, whoever is using a phone to scan, there is no other option. We have to send it to her laptop. So how do we do that without getting flagged? Because I think,
No,
like,
you
if
will
we,
be
even
flagged.
if I
You will
open
be flagged.
a new tab, they will know, because that's how I transfer. I have to transfer through the internet and use something else to download.
Yeah, you can do that. That we have told them that the flag, they will not consider it. They will give all the flag to us, and teacher will decide whether to consider that flag or not. Okay, so it's like a people.
So wait for. Okay. So for
You
that,
just
you have to
ignore the
physically
flag.
look at every student's flags to see if it's all right
No,
or not.
no, no. That they will do only if there is a doubt, right? See what happens. It's like an invigilation only. People are just looking around you. Here it is just a record is kept, and that record would be used if there is any problem. What those people do in this case is give us all the flags for every student, and teacher may consider or may not consider those flags. But your PDF file would be corrected as we do in the VLearn. They will be evaluated, and if you find that at the 10th minute, if you are switching on some tab and doing the mobile call, then obviously it is a problem. But at the last 10 minutes, you will be given to upload, and at that time, if you do fiddle around with your mobile, all those things would be okay, right? You understand? We understand. It's not that we want to punish you for moving around.
Sir, one more thing. I think I've heard that the scanning time is also included in that 90 minutes of maximum duration.
Yes, yes,
So
yes.
yeah, just wanted to let you know, because the number of questions will have to be.
Yeah. No. That 90 minutes is a total exam duration from the clock will start clicking, and then it would go on till 90 minutes, and that's the end of your time. So whatever you want to do, you have to do in between. So you might know that there is some Senate resolution, whatever teachers have been told to do the question paper accordingly, to have it consider everything into account. Right? For example, class test, we gave 2 hours, but question paper was probably for an hour. The 1 hour for you to do all this. Here you are not going to get that much time. It is considered that you should be given at least 10 to 15, no direction from academic office. It's a 90-minute test, and teacher can decide based on that. If teacher want to be tough on you, then question paper can be very long. If not, it could be short. So what I would suggest in this course is 1 hour question paper. Okay, 90 minutes, another half an hour, you would get time for scanning, uploading, and all that business. But be aware of all the flags. Okay, so it is.
Sir, apart from this, when do we have to submit this tutorial, like with this homework that
Yeah,
I'll...
today usually what the time? 10 o'clock. Okay.
Okay.
Keep it 10 o'clock, not 9. That is fine. Because invariably people miss out, give some silly reasons telling that my power went away and all. It's okay when one day is given, but 1 week is given, power going cannot be a reason. I have not heard any place where power going for a week time. Okay, so 1 day is okay. 10 o'clock today. Oh, all this thing which I told story is recorded. Okay. Should not go into public. Might have talked against academic office. Okay, any other questions? Okay, so we'll stop here.